All right, so for this last set of slides, we're going to go over other quantitative techniques. So some of which we've already seen before, but we'll take maybe a just slightly closer look at them. So there's a lot of different techniques that are out there. So far, we've pretty much focused on the general linear model. But of course, statisticians have invented lots of other tools for that apply to very specific problems. So the goal of today's lecture is to be able to match a business problem with a particular empirical quantitative approach. So on the exam, how this typically manifests is I will describe some sort of business question or situation and give you a list of possible techniques, and you say, oh, in that situation, you would want to use this technique. So I think ChatGPT should be able to do this, but I will do my best to not let it, or just maybe I'll try to make it best and not make it too easy for ChatGPT so that you'll have to check it. So here we go. So how this is relevant. So in your job, you may not be doing data analysis, but you may be faced with business problems that could benefit from analysis. And knowing how to use general linear model is a super useful tool, but also there are lots of vendors that you could contact, and maybe they could do some sort of specialized analysis for you. For example, the conjoint people, Sawtooth Software is you might, if you needed a clustering or conjoining type project, you might reach out to them. But you would have to know what you were trying to do before you did that. So, all right. Also, one of the techniques, in particular cluster analysis, is what sort of underlies most of the products that we interact with on a daily basis. So there's, for example, the reason Facebook can exist is because it sells ads, and the reason it can sell ads better than other places is that it mines your behavior and puts you into clusters, and then it promises to marketers, hey, I can put your ad in front of clusters of people who will click on it and be interested in it. So you sometimes often hear this phrase come up: if you're not paying for it, you're not the customer, you're the product. So something about your behavior is being mined, repackaged, and sold. So anyway, that will come in the contrast. So deep thoughts. What is a statistical model? What is the point? So we actually did this during the semester where we talked about, statistical model is usually you have some data at hand, and you want to make predictions. So what if you could create some data with hypothetical scenarios, or look at past behavior, or look at past experiences and use that to predict something. So the simplest model that we came up with when we did this in class is an average, right? So if I know the average height of some population of people, and you said, a baby is going to be born in that population, what do you think their height will be when they are an adult? The best guess would be the average height of that population, right? That would be the simplest model that we could come up with. And so that's essentially what a model is, and they just sort of go up in sophistication from there. So where we mostly spent our time with was looking at lines through a multi-dimensional space. And then lastly, we got into interaction variables, where we said that line, the slope of that line might depend on some other factor. So that's the essence of an interaction, the idea that some cause and effect relationship depends on some other set of conditions and doesn't work the same way every time. And we did mention that was not just for experiments, like clean little 2x2 experiments, but that happens in all sorts of phenomenon. So you could put interaction variables in any kind of regression equation. So if we think that is happening, if we are building a model to predict something, and people say something like, well, sometimes Gen Z likes it, but only Gen Z women like it more, Gen Z men don't, then presumably we would have some sort of measure of Gen Z and some sort of measure of gender, and then some variable there multiplied together, even if we were doing sort of a big survey with lots of different demographic and psychographic predictors. So that's what an interaction allows us to do. So we've seen this in class as well, but it's just a chance to review it and sort of reinforce the point that it's not just experiments. That's the sort of cleanest way to look at it. But these interactions happen all over the place, so they can make their way into lots of different models. All right. So that was just a think, pair, share. Also, next up, variable transformation. So not everything is linear. So again, we've been saying we're shooting a line through a bunch of dots. But what happens if the best fit for that line would actually be a curve? Right, what do you do then? Like say, imagine we have dots that are sort of going up in a sort of exponentially increasing fashion. Well, essentially what you do is you transform the data in order to make it into a line. So if you think you have something that's increasing exponentially, so you're dealing with sort of a hockey stick kind of growth or any kind of exponentially increasing curve, what you would do is you would take the log of everything. So you take the log of the dependent variable, the log of the independent variables that you think are moving in that sort of pattern, and you would then just use general linear model again. But what you've done is you haven't used a different kind of approach. You've just transformed the variables, and then you just have to do a little bit more plug and chug. Say, okay, if we get 3 log unit changes in in x3, what would be the effect on log unit changes in y? And then you delog it, and then you can have some estimates that probably make sense. But that's the essence of it. So if you have there's other shapes, so it's not always just taking the log of something. So a lot of times, sometimes we deal with these inverted U shapes where there's kind of the optimal point is kind of in the middle, and then we start to get decreasing returns, and then sort of negative effects of more. In that case, you would sort of take the square of the thing to straighten it out. So we didn't really get into like the complexities of this in class. We just sort of always were kind of operating the end of the assumption that things were kind of increasing in a linear fashion or decreasing in a linear fashion. And but if you come across this, if you were ever to build models and you were saying, well, that's probably not linear, it's probably curved, what you would do is you would look into variable transformations. All right, ANOVA. So ANOVA is, we've seen before, if you remember, we've seen the word ANOVA on our regression output, and we briefly looked at that. We said, well, what ANOVA just tells us is does your model as a whole do better than chance alone? So almost always we said we don't even bother looking at the ANOVA when we're doing regression analysis, because if our model as a whole doesn't do better than chance alone, we've really done almost nothing, right? So what it's called is an omnibus test. So it tests the whole thing at once. So if you had not just an A/B test, but you had an A, B, C, D, E, F test, for example, then your ANOVA, omnibus ANOVA, would tell you that are any of these things different from each other. Now, ideally, that's not a very specific, prediction, and you can't really do much with that. And then you would probably, what you're wanting to do is actually start making specific pairwise comparisons. And so it's important to note that the ANOVA doesn't comment on any, so pairwise comparison would be, oh, B is better than A, and B and C is better than A, B or whatever. Those are pairwise comparisons. ANOVA doesn't, and then your omnibus ANOVA does not inform that. It just tells you if any of the A, B, C, D, E are different from any other ones. And so you have to be a little bit careful that you don't sort of use that omnibus ANOVA to justify all of your pairwise comparisons. So those each need their own p-value. And ideally, the more of those you are planning to make, the stricter you are with your p-value as well. So I don't really have a slide on this, I don't think. Yeah, no. But remember, the whole idea we talked about behind experiments was that, and p-values in particular, statistics, the whole idea behind statistics and p-values is to keep us from saying something is happening when in fact it isn't. And that is the idea of a false positive or a type 1 error. And so the thing is, the more tests we do, the more statistical tests we conduct, and the more things we look at, sooner or later we're going to find something that looks like something is going on just by chance alone. So in an A, B, C, D, we could theoretically compare A to B, A to C, A to D, B to C, B to D, C to D, and do all those comparisons. And so in that case where we have 4 or more A, B, C, D, E, we have to start being stricter with ourselves in terms of the p-value. So in the same way that we could be, more relaxed with ourselves in the p-value when we were talking about directional hypotheses. Remember, we had that case in linear regression where we said the only path I'm willing to accept, the only coefficient is a positive coefficient. In that case, maybe we don't have to hold ourselves to 0.05. Maybe we could go up to 0.10. The opposite works if we're like, oh, we're gonna collect 10 different versions of something and root around in those 10 different versions for any single pairwise comparison that might be different. You have to be kind of careful about that as well. And in some sense, there's this thing called a Bonferroni correction, which essentially takes your 0.05 and then starts dividing it by how many comparisons you're planning on making, which we didn't really get into, but just maybe wanted to make you aware of in the end here. This ANOVA thing that we have seen is an omnibus test that tests whether any of the things are different from any other thing, which isn't a very specific hypothesis, which is always why it's statistically significant. All right, ANCOVA. So ANCOVA, how is that different from ANOVA, is with the inclusion of a control variable. So remember, the idea behind a control variable is it's something that's not really the focus of our study, but something that's probably important nonetheless. So one example that came up in class from somebody's project was on impulse buying, and their theory was that exposure to social media leads to increased impulse buying. But there's probably also the case that disposable income also is important when it comes to impulse buying, because if you don't have any, probably even if you would like to impulse buy, you maybe restrict yourself a little bit. So that's boring though. Like saying money determines buying is not interesting. It's interesting to saying watching TikTok videos from Alex Earl influences buying. But we may need to put that control variable in there nonetheless, because it probably does have an effect. So we include it in the regression analysis, or in this thing called ANCOVA, to control for that thing that probably matters, even though it's not really the main narrative of our story. Chi-square analysis. So you may have seen a chi-square analysis if you took data analytics and did pivot tables or crosstabs. So chi-square is the situation that would drive use of chi-square is if you have a dependent variable that is a 0-1 variable. So typically like a choice variable. I picked it or I didn't pick it. I voted for this person or that person. And also the independent variable is usually also like a categorical variable. So let's just say like gender. Right, so there's a lot of press in, coming out to the election about whether different genders voted for different political parties at a different rate, right? And so what you could have is you could collect data where you collected someone's gender. We'll just imagine for the time being that we have males and females. And then we have Republicans and Democrats. So a simplified view of the world. And so that creates 4 squares. So you would look at the first, so let's just say, for Democrats, 50% of them were male, and 50% were female. And then maybe you would look then at the column for Republicans, and if 50% were male and 50% were female, then you would say you would get an insignificant p-value because the ratio is 50-50 in both cases. If one time the ratio was 60-40 and the other time it was 30-70, then that would be a different ratio, right? And so that's what a chi-square does. It does it instead of having continuous variables predicting continuous variables like we normally like in regression, where we have normally distributed independent variables and a normally distributed dependent variable, and we look for those things to move together. This one, we have 0, 1 variables on one side and 0, 1 variables on the other side, and we do what's called a chi-square. And it's essentially the p-value is relating to looking if the ratios are different rather than if the slope is different from 0. All right, cluster analysis. Who, what belongs together. So why we might want to use cluster analysis. So this comes up in marketing situations quite a bit. So market segmentation would be one. So we have customers who buy our stuff and we want to know who the customer segments are. So we would want to cluster them into groups, or we have competitors we want to cluster. So sometimes these are referred to as comp sets in different industries. So we want to have a benchmark ourselves against different competitors. We might do the same thing with them. Or just we have big data and we can do something with it. Right. So what it does is it cluster analysis finds people that are close to each other on several dimensions, and there are many different algorithms for doing so. But different approaches, I should say. But more interesting, so there's a flower on this because the classic clustering, when you learn clustering, there's this data set called the iris data set, and it has these different attributes of irises, and they test them because these turns out this is how you determine what families the irises emerged from. And so they test historically clustering techniques on this iris data set. But where that's sort of esoteric, where what's more important to you guys is that this is also the method that Pandora recommends songs to you, that Netflix recommends songs to you, that Amazon recommends products to you. They're just clustered together. Oh, people who bought these products tend to cluster together. They're also how Facebook clusters people together and creates, it's been a while since I've heard, but at some point they were maintaining over 1,000 different clusters, 12 or 1,500 clusters, and they would match those clusters with particular products. So they would put ads in front of clusters that they thought would click on those ads. All right. Conjoint analysis. So conjoint analysis will appear on the exam. It's also sort of the concept behind it we've also talked about it in the context of why experiments are an inherently limited technique. So the idea is, remember, if we're doing full factorial experiments, we started out with a 2x2. Okay, we want to have technology, or we want to have a short, let's do the line example. We're going to have a short line or a long line, and then we say, okay, well, what if we have it's an unknown service versus a known service, and it's okay, that's fine. Well, what about if it's and then that was 4 possible combinations. And then we say, okay, well, what about if it's unknown food versus unknown food? So then in order to recreate all those initial 4 conditions, we would have to then do all of those 4 at an unknown food type and all of the 4 at a known food type. So then we would have twice as many. And then let's say if we wanted to do 3 different price levels, low, medium, and high. Well, then we have to create all 8 of those at each of those levels. So now we have 8, 16, 24 different conditions. and assume we have to have 100 people in each one because we think the effects are small. It exponentially increases. The idea behind experiments, when we talked about it, is each additional thing you add, you exponentially increases the possible combinations. So you may remember like permutations and combinations from statistics in high school, right? Although that's probably not the best way to approach this question. But anyway, you may find yourself in the situation where you have too many possible combinations to test each one in a full factorial kind of way. So what conjoint does is it presents like subsets of those combinations and asks people to rate them or rank them, and then uses some statistics to see which features contribute to the overall utility. So for example, let's say we were Procter & Gamble and we want to introduce a new product, and there's 7 different attributes. We can change the brand, the flavor, the color, whether or not it has moisture beads, the size of it, and whether it's a transparent or rounded bottle, and 2 price levels. So if you were to imagine that each of these things has 2 levels, so soft soap versus, I don't know what another brand of soap would be, Dial. So pomegranate and mango versus cherry, red versus blue, moisture beads versus not, 18 versus 16, transparent versus not transparent, and it's $5 versus $6. All right. To come up with all the combinations, that would be like a 2 by 2 by 2 by 2 by 2 by 2 by 2, which would be 2 by 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, times 2 is 128. And so that would be all the possible combinations we would need to do. So if we wanted to do, we couldn't possibly mock up 128 different conditions in a sort of a lab study. It would be just impossible. So you would have to turn to this thing called conjoint in order to present a smaller subset of the features. So a classic example in this is like airlines with different features. Like airlines use this a lot to figure out what drives utility for different combinations of different features of a flight. So they're called utility weights. You can rank them, so as you might expect, sometimes these are really closely rating. They might achieve the same rating because they're only varying by one of these attributes. So another option in this space is to use ranking. So we've often saying here rate, don't rank. The exception being that when things are so close that they would all be tied, you can go ahead and that's when it makes sense to use ranking, because if otherwise they all would have received a 7 out of 7. So if everything's going to receive a 7 out of 7, then you need to sort of use ranking, even though typically we don't. All right, discrete choice modeling. So discrete choice modeling is sort of another flavor of conjoint, but instead of rating or ranking, you're picking. So, and what this allows you, because picking is a behavior, it allows you to estimate market share. So you could put in a bunch of competitors and your offering, and then have people pick, and then you can use that to estimate what the market share of something would be. I did ask ChatGPT to explain the difference, how I might explain the difference between these two, and here's what it suggested. Conjoint is like a mix and match game, and create different combinations of phone features and ask people to rate how much they like each combo. The goal is to see how much each feature matters. Discrete choice modeling is more like a this or that game. You show people 2 sets of phones, phone A and phone B, and ask to pick the one they'd actually buy. It mimics real-world decisions where you choose one option. And then I said, which one is better for estimating market share? And it correctly said, discrete choice modeling is generally better for estimating market share, and here's why. And so So if you are ever struggling to like understand the nuance between why you would use one of these things, you can just say, have explain to a 16-year-old what the difference between conjoint and discrete choice modeling might be. All right, meta-analysis, or p-values more generally. So we also talked about this briefly, I think, in experiments, but we sort of glazed over it, so we'll revisit here. So a meta-analysis is a way of combining studies that are very similar, and you could sort of combine them. This angry baby on the bottom here reflects my reaction one time when a reviewer, we handed in some studies, and the reviewer said, well, this time it was 0.03, so 3 times out of 100 you would get this chance, you would get something this extreme by chance alone. But when you repeated it, you got a 0.06, that there was a 6 times out of 100 you would get something this extreme by chance alone. So then the moron proceeded to say, well, essentially it worked one time and it didn't work another time, so essentially what you're looking at is a 50% chance of observing something. And I about lost my mind when I read this, because I don't know how you go from a 3% chance of seeing something and a 6% chance of seeing the same thing the second time and getting to a 50% chance of seeing it. It's because the guy was a moron and just was didn't understand the concept. But anyway, what the p-values do is what meta-analysis do is it combines them. And so if you saw something that was extreme one time and you saw nearly the same thing again, you would be even more convinced of this thing, not less convinced of this thing. So when we're looking at p-values and we say, oh, it's a pretty good looking p-value this time, and also, oh, it's a pretty good looking p-value this time, we become more convinced. So one time I did a study with the use of emojis in texting and click-through rates, and the effect, it turns out, is like negative because people perceive emojis. The theory is people perceive emojis as being sort of like a persuasion tactic, like, oh, why are you trying to get me to click on this message with your weird like 100% and exclamation points and fireworks and party horns and stuff. So they click on it less, but it's a really small effect. So what we had to do is we had to look at like 100 of these different campaigns, and when you look at 100 of them, over time, it turns out over time that a small effect adds up to something that's statistically significant. So essentially, the way you interpret this thing right here is called a forest plot, and each of the horizontal lines is a study. And essentially, the length of the horizontal line represents the confidence interval. And anytime the confidence interval crosses the vertical line in the middle, that means it was statistically insignificant. And so you look at the one at the bottom, it clearly is statistically insignificant. The one up next to it is also statistically insignificant. The one closer to the top, almost statistically insignificant, and the one at the very top is statistically significant. It would be below 0.05. So so you have 2 that didn't work, and then one that almost didn't work, and the one that worked. But if you look at the combination of those, which is the diamond at the bottom, and you look at those all together, it's quite clearly far away from being statistically insignificant. There's no risk of overlapping. So the horizontal line for the diamond is much narrower because that's the bigger sample size. So as we have a bigger sample size, that's one of our 3 ingredients, right, of a p-value. So we become more confident. So we have those confidence intervals shrinking, and then the diamond shows, well, yeah, sometimes it doesn't work, but on average it does. We would expect it to work. So, all right. Eye tracking. What are you looking at? So this is something, eye tracking, if you're interested, Dr. Larry Carter teaches a class on this called Biometrics for Business, where you learn how to run eye tracking studies. And essentially what you do is you learn what grabs people's attention on a screen. And so you can Google this, and there's lots of interesting examples of it, or watch the video. But essentially that can be super important. Sometimes it's just funny. So this is from Business Insider eye tracking heat maps, and we can see when people look at different things. But sometimes it can be super useful strategically. So you may there's like a genre of TikTok, or not TikTok, like YouTube prank things where they put an eye tracker on people and then put like try to get them to look at people's butts and stuff. I don't know. Anyway, never mind. Let's think about how we would use it in marketing. So in marketing, if you can look closely at the video here, you see in one of the ads the model is staring back at the viewer, and another one the model is looking at the product. And you could probably make a conceptual argument by either might be good. You might say, oh, well, if the model's looking right at the viewer, that's probably very engaging, and so that would be good. Or the other argument, which seems to bear out more, is like, well, if the model looks at the product, you're probably also more likely to look at the product and then actually know what the product was. So that's what happened in the one on the left. When the model looks at something, you're like, oh, maybe there's a tiger over there, a saber-toothed tiger I should be looking at. So turns out this is an evolutionary thing. When other people look at something, we also look over to see if there's some sort of danger that we need to pay attention to, like a herd thing. So anyway, when the woman looks at the product, the viewer looks at the product and makes her way up to the thing, and so up to the tagline, and so this ad on the left probably performs much better. We might not have known that, or without the eye tracking, or at the very least we might not have known why it works better. You can also follow these in order, to see how people use different things. There's other kinds of things, ways we can plug people into machines, so other biometrics. And so the driver behind these is that people don't always answer surveys accurately for a number of reasons. And so if we just hook them into a marketing research machine, then that sort of bypasses a lot of the sort of demand effects and biased responses and self-presentation motives and all the kind of stuff that get in the way of accurate research. So there's a number of different machines we can plug people into. You saw the eye tracking machine, but the other biometrics might be like an MRI, where we can see activation in the brain. Galvanic skin response is a little device you put on someone's hand, and it measures how long it takes the current from one finger, an electric current, to go from one finger to the other. So essentially, as you get sort of to have psychological arousal, you sweat a little bit, and that your skin becomes salty and wet, which improves conductivity. So this electrical signal goes from one to the other much quicker. If people are stressed, you can do a swab of this inside of someone's cheek and measure stress levels or cortisol levels. An EEG is a device you hook to someone's head, and it sort of again measures blood flow in the brain, but specifically maps it to different emotional responses, or emotion and sort of activation at different types of processing. So anyway, that's my lecture on different types of techniques. How this manifests in the exam is I will just present some sort of business problem, and you will say something like, oh, for this business problem there exists this tool called a meta-analysis or a conjoint analysis or a eye tracking, and you say we should use that. So that's the key takeaway for this lecture, is to sort of for you guys to know what statistical tools go with what types of business questions. So all right, I think that should more than do it for the questions on this exam. As always, check ChatGPT for accuracy, and good luck.